Okay, well, thank you for attending. This is a talk about what I call it's an anti-pattern, which we call a revolving door. And we'll get into the guts of everything so that we can explain what all of this is. But um, the motivation for this talk is that this is something that I've seen showing up on a more regular basis in a number of different places. So I just thought, hey, this is interesting. Let's just talk about it and see what's going on here. Now, hopefully the pacing of this will be good, so that we'll get through it within in the 30 minutes or 25 minutes that we have left here. Anyways, so there's an about me slide that's up there. I guess you can just read the whole thing. We started writing diagnostic tooling for a company called J4K. The banner's still on the side of the slide deck for whatever reason. Microsoft onboarded us, and we're continuing to create this what I call diagnostic engine, which we call Illuminate. It's based off of some methodology work that I've done. Other things, JCREAT is an unconference that we organize in the summer. Unfortunately, for the last, it's given the current conditions, we haven't been able to hold it regularly. But anyways, be that as it may, hopefully we're going to get it restarted really quickly. So I want to start this talk by basically saying, okay, what's a design anti-pattern? What's this anti-pattern stuff about, right? Well, I think if we're going to understand what a design anti-pattern is, let's actually look at a design pattern first, very briefly. And maybe most of you are familiar with with this thing, like a design patterns. They're commonly used, but we'll just review it here anyways. So if we look at a design pattern, what we're looking at is we have a problem, and we're going to take that we need to solve, and there's some context in which we need to solve this thing, and there's some forces that are also acting upon us. And we combine all these things together, and we tend to end up with a solution to the problem. And there's going to be benefits and consequences, and maybe there's other things that we could have done, or there's related solutions that might fit this particular scenario. Right. So that's basically how we write software, right? Now, what happens is that if we start seeing this same situation occurring over and over and over again, then we can document this as saying like, hey, I'm seeing this pattern show up over and over and over again. And what I want to do is I just want to make everyone else aware of it. We call that design patterns, and we can put these design patterns into catalogs, right? So what you see is that a design pattern is this reusable template for a solution to a commonly occurring design problem. Applying this pattern to the problem generally leads to a good outcome. And more importantly, it gives us a language for describing our designs. So I can talk to you about the factory pattern, singleton pattern, adapter, command, double dispatch, and so on and so forth, right? So we can just keep talking about these patterns, and as soon as I say, hey, we use double dispatch or adapter or whatever in here, then that gives you an idea of how I've structured the code, right, or what my design principles are. So this notion has been around for quite some time. It goes effectively back to the 70s, but was really popularized by the Gang of Four book, where they just talk about patterns and design patterns, and they come up with the language of patterns known as plop, and there's these plop, so there's all these people talking about these things quite often. I think the thing that comes out of here is that it really sets out a standard template to help us categorize and describe design patterns. And so these are really nice, right? So if we're going to have a pattern, of course, why would we not have the anti-pattern? And, just as the pattern gives us a solution that leads to a good result, the design anti-pattern is a template for a solution for a commonly occurring problem. And we're going to apply the solution to maybe to some new context or whatever, but we're going to transfer this thing over and we're going to use it again. And, or maybe we've just thought, hey, this is a good solution to this particular problem. But when we start applying this pattern to this problem, because maybe that's a naive or like the first principle approach at this particular problem, we're looking at it saying like, that's going to lead to some negative consequences, right? So we're going to have this anti-pattern template. We're going to describe the general form of the anti-pattern, the primary causes, the symptoms, the consequences. And typically at the end of it, we're going to say, well, if you're in this situation, maybe you should have done this. And here's a pattern that generally will lead you to a good result and away from these negative consequences. So if we go back to this little diagram, we can see that we have the solution, we drop it into a new context, it becomes an anti-pattern. There's symptoms and consequences of all of this. And again, you're going to have benefits and consequences of the refactored solution. Yeah. So that is really what we're talking about, is that people are applying these software design principles in a way that results in something negative happening. And I would say an example of this would be like a DTO. A DTO is a pattern that we'll look at later. And DTOs really came out of the EJB world, where we had an issue with how we were accessing data. So the DTO solved that. And then all of a sudden, people started using that as a pattern for decoupling. Unfortunately, it doesn't really decouple, and it leads to other consequences. So you end up with it becoming a design anti-pattern. Right. Now, getting into what is a revolving door, and right. So where did the revolving door come from? Well, I think we've all pretty much used a revolving door, but maybe we don't know much about the history of them. So I just thought for fun, I'd throw this in, right? So it's invented by this guy, Theophilus van Kannel. I hope I didn't butcher his name too badly. In 1888, he only gets to start a company producing these things about 10 years later in 1898. And, they become kind of stylish. And so you can see buildings built around that time, and going forward, put a lot of architectural design into how they build their revolving doors. Now, why did he, or, what was the motivation for inventing this? Well, there's somebody suggested it was preventing horses from entering the building through the regular door, I guess, which is kind of silly, and it was, struck down. But it turns out that Theophilus didn't like the social etiquette of doors, like opening it. And in particular, he didn't like that he had to open doors for women because he had some mother issues that you can read about on the web. It turns out these doors are fantastic for energy conservation, and they help moderate foot traffic. So there's all kinds of wonderful benefits for using the revolving door. And, so they're with us today in different forms. Now, how do we turn this actually into a software design anti-pattern? Well, here we're going to use a shortened version of the template to basically describe this thing. So a revolving door is, what I'm going to do is I'm going to drag data over an expensive barrier that's going to trigger what I'm going to call voluntary context switching, right? And that's, well, really, we don't need to have that last part happen, but in today's talk, that's effectively what we're going to talk about. And I'll get into defining what some of these things are as we go through the talk, right? So the motivation is a local calculation needs data from a remote server. This is like EJB. What happened is that the client would need bits of data. So it would say, get X, get Y, right? The applicability is the data is retrieved one element at a time. And the consequence is the calculations engage in a large number of high latency calls. And to give you an example of this, before I get into the two examples that we'll look more formally at, we had one application where, they get into this high latency call. I mean, the latency was less than 2 milliseconds, but they did 20,000 of these. And as soon as you like 20,000 times 2, you can go like, okay, that's 40 seconds of latency just by how they managed their call sequence to get the data that they needed for this particular calculation. Right. Known uses. ORM mapping tools will accidentally use this, especially if they're trying to do joins in the client as opposed to performing the join in the database. And as it turns out, microservices are prone to this particular design anti-pattern. And I guess one of the reasons why we're seeing them occur more frequently is because, well, more and more people are moving to microservices style of architectures, maybe without understanding fully what the impact of some of their design choices are on the underlying hardwares. Now, I would say that, if we roll this back into Kubernetes or Docker or anything like that, or basically we're running a virtualized running it in a virtualized environment, then as you're going to see later on when we look at the mechanisms, that these environments actually add a slight little bit of stress to the activity that is being aggravated here, which means that the performance impact gets magnified. Right, so here's a solution. We want to bulk up our retrievals. And the way we're going to do that is one of the patterns we'd use, like a DTO. So in EJB land, we couldn't serialize the EJB to bring the entire thing over. So we just have a client API that we'd make a call to, and we basically say, give us everything. So it all comes back to us as a data transfer object. All right, and as I mentioned before, DTO eventually becomes an anti-pattern. Okay, so let's take a look at a couple of cases of this now that we've seen what the anti-pattern is, and hopefully you'll be able to follow along and recognize what's going on here very quickly. Okay, so we're called in to look at this service, right? Now, the service is performing well when we come in. The problem is in the consequence here is that the COGS, or the cost of goods sold, has increased to the point where we've taken this service that was in the black down into the red, right? So it's a losing service, and the COGS have increased because of the increased memory footprint, right? That for their applications, right? And this comes from, okay, the symptoms. They said the client stalls and was suffering from stability issues. They looked at it. They really couldn't sort out what was going on. They figured, you know what? It's generally Java applications got to be garbage collection. So that's a memory issue. Give them more memory, everything was fine. And yeah, that worked, right? They got improved performance and stability. But as I said, the cost was that their COGS increased because of this. Now, that's what we're told up front. And so when we start digging in and we try to figure out the things that are, that we weren't told, what they said was that, oh, we increased the memory footprint, and that forced us to move some of the servers onto more hardware, right? So they had to get more virtual machines and different size virtual machines, and that's where their costs rose. Yeah, so they just had more machines. So we look at that and go like, okay, and this is an important clue as to what's going on. Because now if we look at some of the data that we initially collect, we just sort of get on the machine and said, okay, let's just get an indication of what's happening with the hardware counters when the server is busy. And you can see, so there's a whole bunch of columns here. They all have all kinds of different bits of information here. And initially, the important ones are these three over here, which is our user time, system time, and idle time. So it's a breakout of how the CPU is being consumed. And you can see there's two other columns over there, like weight and steel, but we don't have to consider them for this particular problem. Out of interest, weight is basically process spinning in a core, and it's spinning there waiting for something to complete before it can go forward. So the significance of that is that the core isn't doing any useful work, but the core is also not available for anybody else to use. Steal time is what happens when one virtual machine comes in and says, hey, I want more CPU frequency, therefore I'm going to steal it. And so if you're the victim of that particular action, then at least you will be reported of it, and you'll be able to see that, hey, some other virtual machine's been stealing CPU cycles from me. But anyways, those are all zero there. So everything is nice and fine and dandy on this point. But we can see that here we have a user time of about, eyeball estimate, 25 to 26, 27, something like that. It's just over 25%. That's the user time, right? So that's the straight up application time. Now you have this other column, which is system, and that's the kernel time. And the kernel time here is around, say 4%, right? Or 4 ticks out of 100. And we have a whole bunch of idle, like well above 60% idle most of the time, right? And if I go all the way over to the left of this diagram here, you can see that I have an R, and that's a runnable queue. And you say like, hey, look at that. There's all of these tasks that need to be run. I have idle CPU. Well, why are they not getting there? Why is my runnable queue not running? All right, and now you have to think that, okay, well, there's something else going on here. Also, if we look at the breakdown, right, I said this is probably, use a rough estimate like 5%, 25% for user system time. He's looking at you look at this and go, well, the kernel time is actually consuming 20% of user time, right? So that means that I'm doing a little bit of user work, and then I'm doing a significant amount of kernel work. And when I say significant, that means that I consider anything where this ratio is greater than 10% approximately. I'm going to say that that's my application asking my operating system to do a lot of work for me. Now, why do I care? Well, I generally care because the operating system tends to run things single-threaded. And then you get hit by Amdahl's law, which basically says if I'm running serially, my performance is going to get my ability to saturate cores is going to decrease, right? My ability to parallelize this work is going to decrease. And effectively, that's what we're seeing here. But we're not seeing this at an application level. We're seeing this at a hardware level. And this goes completely across the entire piece of hardware. So that affects everything that's running on this machine. And that's possibly why the idle time is so high. Here, so we can see our runnable queue, as I pointed out before, right? Now, the other thing is that, okay, you have to ask, it's like, okay, if the kernel is running hot, then what is it doing? And to me, this looks like a scheduling problem. This is actually a thread scheduling problem, right? And we can get a better hint of that because if we look at the context switching rates over here, we can see that they're greater than 70,000 context switches per second. And that really confirms that we have a thread scheduling issue here, right? Now, interestingly enough, we had all of the users log out of this particular app, so it basically shuts down. And if we look at this one here, and I'm sorry about the quality of the graphic here, but if we look at the context switching column in this particular graphic, we'd see that it's well above 80,000. Yeah, so we have like more than 80,000. So, you know, like what gives? The users have logged out, our context switching rates have gone up. You know, so like what? You know, what's going on here? Okay. And if, okay, so let's put this one aside for now. And let's take a look at a second one that's in a pretty similar situation, right? Service is performing poorly, client waits minutes for simple web access. You know, there's not too many clients here using this particular web app. It's an in-house specialty app for scheduling things. Action taken, none. Right, benefit, well, I just trying to be funny, said decrease development maintenance costs. Yeah, you can laugh later. Consequence, project is canceled. So I'm actually called in this case, after the project has been canceled to see what we can do to see if we can convince the people who have canceled it to uncancel it. Yeah, so in the initial investigation, you can see we got this little Windows view here. You know, it's a simple 3-tier application. So just browser to web app to the database and out and back. As I mentioned before, in-house, so not many people using it at any one point in time. And then we start like poking around and we're trying to get time budgets to figure out, okay, so what's going on here? So we look at database, of course, sub-millisecond, so no problem there. Network is completely devoid of any issues. And, you know, we look at the CPU chart from the server. It's like a very bad screenshot. So, but you get the hint that, you know, that with the red line being the kernel and the green line being the user time, you can see that what we've done, we're in this situation again where, if, you know, do some estimates on what these levels are and the ratio is about 40%. And so 40% is well in excess of that 10% threshold. Okay, so this is obviously when running on a Windows server. The last one's running on a Linux kernel. And you can see that really, even though we have these very seemingly different operating systems, you know, at the core here, we're running into the same issue with both of them, which is actually quite interesting. Right. So now the question is, you know, so we have this excessive pressure on the operating system, and, you know, so, you know, what do all of these things have in common? Well, they all have problems with thread scheduling. And how do we get this problem with thread scheduling? Well, we get this problem with thread scheduling because we have many small tasks that are completing very quickly, and that's placing a lot of pressure on the thread scheduler, and that's hyperactivating the kernel itself. So this is why the kernel CPU numbers are as high as they are. So there's two questions, right? You know, why is 10% considered a threshold, high threshold? As I mentioned before, this is I mean, this is a consequence of Amdahl's law. Why is it 10%? Well, this is from our observations in the field, and we've done some machine learning work afterwards to confirm that it's not quite 10%, but you know, this is a number I'm going to remember. And it's not constantly 10%. It does fluctuate around, but this is a number I'm going to remember. So I'm just going to use 10% as a gross rule of thumb, right? Yeah, so the question is, what is the system, you know, so what is the system being asked to do, and how much does that cost? Well, as we mentioned before, this is a thread scheduling issue. And so if we go and look at thread scheduler mechanics, we're going to find that dividing CPU cycles amongst tasks is a complex problem that you might think is solved, and it is in a lot of cases. I mean, it's very efficient. It's been well worked on, right? But it still has some fundamental flaws and fundamental problems in multiprocessing, multi-core systems. You know, first we want to try to select a time quantum. So that's the amount of time that my thread gets the core for before it gets bounced out. And we need to set that to balance between responsiveness and the cost of context switching. Now, the context switch itself is a very quick operation. It happens in a matter of, handfuls of clock cycles. The issue is that it tends to leave the caches out of alignment with what's going on with the thread. And when you get into that situation, you have to now do a lot of fetches from memory. And, without getting into a lot of detail here, the estimates have been that a context switch can cost your thread upwards of 80,000 clocks. And you think like 80,000 clocks, so that's a significant number of clocks. On a single core, you have 2 billion of them to play with, or, for a 2 gigahertz machine. But anyways, you can start doing the math and try to figure out, like, wait a second, all of a sudden, I'm burning a lot of my CPU simply managing the threads. Now, the scheduler itself runs on core 0. So it's just going to load the tasks up, right? So it basically says, okay, here's all the work I have to schedule. It's like bang it all up into these task queues. I'm going to have a task queue per core. And then it's going to have the cores like burn through their task queue. And the scheduler itself is going to schedule itself to run back on core 0. So when it's scheduled to run again, it gets in there and it basically resets all of the queues again, and off you go again. Which gets into the question, if I have all these very, very short tasks, where does that leave the cores when they've burned out their queue? Once they've run out of queue, they're idle. That's it. Right. So a little bit more of the mechanics here. When the time quantum expires, the task is going to be said to be involuntarily context switched out. Right? So under these conditions, the rate of context switching is inversely proportional to the time quantum. And this is a very predictable situation. So the thread scheduler is able to tune it, it's able to manage things so that it can always keep things going. So if it's predictable, it can say, well, I need to do something here in order to have it done, in order to keep feeding the beast. If a task blocks or it has a very short unit of work, right, then the task is going to voluntarily context switch out. So there's a difference here between involuntary, which means I've just used up my time quantum, or voluntarily, meaning I've either blocked, so I'm not doing anything useful, or I don't have anything more to do. Therefore, I'm relinquishing the CPU to something else. Now, in this case, the rate of context switching is inversely proportional to the size of the unit of work before the task completes or blocks. And this is a completely unpredictable case, and that leaves the thread scheduler to always be reacting to it. And while it's reacting to it, these cores are going to idle. They're not going to be doing anything. So if we go back to case study 1, we can see the increased rates of voluntary context switching are that's going to hyperactivate the thread scheduler, and that's going to heat up the kernel counters. So that's why they're going to be high, and it's going to leave cores idle. Now, this is really funny. What's funny in this particular application is that everything is still working. It's just that they're looking at the clients to feed them work. And because there's no work coming in, it's just basically, do I got any work? Nope. Do I got any work? Nope. Do I got any work? Nope. And you can see that I have effectively dozens of threads doing this, and they're involuntarily context switching. So the context switching rate is going to go up because there's less to do, but you can see that the idle time is also going to go up because I'm going to burn through my queue quicker. So it's really kind of this weird thing where you have two numbers that you would think would, if one goes up, the other should go down. They are both going up together. And that's just simply because of the mechanics of how the system works. And this is an example of the revolving door antipattern, because what I'm doing is I'm just spinning over this barrier, right? This barrier is in every single critical path in my system. In case study 2, what we had were many small calls to the database. So effectively, we're doing like get table, and for I equals 1 to size a table, get other data value in another table and join them together, right? So the database and the network were very capable of managing this. They were able to scale to that really, really easily, right? But the client itself just spinning over the network interface. And he's spinning over the network interface, like just grabbing data, grabbing data, grabbing data. And it wasn't doing very much with the data. So we have small unit of work followed by block on network call to get the data. And that gives us like these high rates of voluntary context switching. And so this is yet like another example of the revolving door anti-pattern, right? So the conclusion here is that our thread scheduler is a shared resource in a system. And we need to note that that not the app, but all apps running on the same system are going to be affected by this, right? Because this is, in the critical path of every single app that's using the thread scheduler, which is all of them. Also, hypervisors are going to increase the amount of work that the thread scheduler has to do, because the hypervisor is basically there trying to balance the work between the virtual machines. And so it's got to inform the underlying thread scheduler that, hey, this is, these are the preferences that I have to do. Now, in a type 1 hypervisor, where, we can talk about the different types of hypervisors, but in a type 1 hypervisor that's more separated from the operating system, then obviously there's a longer path there. So you get a hit. And this is much improved when we get into a type 2 hypervisor, because, that's basically the hypervisor, that aspect of the hypervisor is down in the lowest level of the kernel, and therefore it doesn't have the same barriers in order to provide the information that it needs to provide that the type 1 virtual machine, or sorry, hypervisors have to use, right? And so it's like more work equals longer service times, equals hotter kernel, equals slower application. So the revolving door patterns of work will inflate voluntary context switching rates, as we've seen. They're going to place the thread scheduler in a react mode and not a predictive mode. We're going to idle our cores. And as we've seen before, we're going to heat up the kernel. So the kernel is going to be running hotter than it should. And this is not a service that's parallelizable. I mean, it's one of these things that it serializes everything. And really the solution to this is to bulk up the size of the unit of work. And how you're going to do this is depending upon your situation. In the first case, what we want to do is we just want to make sure that what we wanted to make sure was that all of the events that were coming in the system were like bulked up, so that that they could be managed by one thread as opposed to being managing by one thread per event. In the second case, we certainly wanted to stop this doing the table join in the Java virtual machine, and we pushed that work out to the database so that we could pull everything in. In the first case that I mentioned, where we had the 20,000 calls, in that case, we've solved that particular issue by changing the framework so that we can manage everything within 3 calls. So again, it was like optimizing the connection between the application and the database, by just hand tuning the SQL. And in the EJB world, like I said, we managed to add a DTO, and the DTO would just gather up all the data that you wanted in that get, and it would just grab it in one shot, and then it would deserialize it on the other end so that the application would have more local access to the data in a one-shot fashion. Right. So I guess that's pretty much all I have to say on the subject, except for, I think in the microservice world, we see this happening more and more frequently because just of how the work is partitioned and we're seeing that maybe the units of work that are being pushed forward are being very, very small. And since we're getting thousands or tens of thousands of these requests per second coming into a system, we're starting to see that the scalability of these systems is affected by simply by the thread scheduling activity. And I think as one note is that most people don't think of the thread scheduler as being part of their application, but when you start thinking about everything that's happening, switching to this mindset where the thread scheduler is part of your application, and not only that, it's a dependency that ties you to the other applications that are running on the hardware. I think that starts making sense, and that could possibly change how you might architect something, or how you might decide to bulk up on work to satisfy your latency needs, requirements, reduce your cost of goods sold. Right. With that, I think I am done with the primary presentation.